Yes. Okay. So before sessional, okay. So we were discussing about the duality. Okay. So let me complete that topic just by taking one more example. Okay. And then we'll switch to the next topic. Okay. So today we first see one example of conversion from primal problem to dual problem. Then we see how to formulate the graph coloring problem using linear program. Okay. And then today in this sessional next topic that we will study is approximation algorithms. Okay. So let us first finish the earlier things. Okay. So as you know that this is what we have discussed. If primal is maximization, dual will be minimization. The variables of primal are related with constraints of dual and vice versa. Right hand side of the constraint deals with the coefficient of objective function and vice versa. Okay. And this A matrix made up of coefficients in primal, it turns out to be A transpose in dual. Let us try to understand this thing by one more example. Okay, so we seen in the last lecture direct one answer that if you want to convert from primal to dual, this is what we can do. Okay, so if this is the problem, this is a direct dual, but how it came and why it is correct, let us see that. Okay, so let me revise that. So minimize 8x1 plus 5x2 plus 4x3. There are 4 constraints. See, the constraints are equations greater than equals to, less than equals to, all types of mixed things are there. Variables are also mixed type of variables. Some variables are positive, some are negative, some are unrestricted. Okay. So for this type of primal problem, what would be the dual problem? This is an answer actually. And then we will see how this answer came. Okay. So what we will do is primal is minimization, so dual will be maximization. Okay. You take the right hand side of the constraints. There are 4 constraints. So I'll take a right hand side. So 12, 9, 10, 7. So I write 12a plus 9b plus 10c plus 7d. Okay. Now I want to maximize this objective function value. Now you see A, B, C, D, what values actually they should take. So that depends on the constraint, because constraints in primal related to variables in dual. So you see the first variable A, it refers to the first constraint, which is equals to type. So remember, whenever the primal has an equation like 4x1 plus 2x2 plus 8x3 is equal to 12, this is an equation. The corresponding dual variable is unrestricted. Okay. So whenever it is an equation, corresponding variable is unrestricted. So second constraint of the primal related to second variable of dual. Okay. Second constraint is greater than equal to type. Okay. And for minimization problem, this is a normal scenario that constraints are generally having this sign greater than equals to type. So the B variable is normal in the sense that it is non-negative. Okay. Same way, the last constraint, okay, is inequality with a greater than equal to sign. So last constraint is related with variable D in dual. So again, B and D both will be greater than equal to 0. Third constraint relates to C variable. And third constraint is, you see, the inequality is less than equal to, and which is uncommon for minimization type of problem. So the variable is also unusual in the sense that it takes a negative value also. So C takes a less than or equal to 0. Okay. So remember the equation with equals to sign, then corresponding variable is unrestricted. Okay. Then since it's a minimization primal, greater than equal to type of constraints are desirable. So corresponding variables would be greater than equal to 0. But if it is a reverse nature constraint, then the corresponding variable will also be reverse nature, that is less than equal to type. Okay. Now let us see the constraint, this thing, okay, that we have seen. Let us, so the first variable, okay, makes a first constraint, okay. So 4 plus 4a plus 7b plus 8c plus 3d, okay, and 8 is there, okay. Now you see the variable, this first constraint of dual is related with x1, and x1 is greater than equal to 0. Since x1 is greater than equal to 0, corresponding inequality sign is normal. What do you mean by normal sign? For maximization type of problem, normal sign is less than or equal to. Why it is so? Because x1 is greater than equal to 0. So the sign that you are going to put, it should be normal with respect to this maximization, which is less than equal to. Same way, second constraint, you can write it like 2a plus 5b plus 5c plus 7d. But you see the second variable is unrestricted in primal. So the second constraint is equals to sign, equation. Okay. And that 5, right? Right hand side is 5. Same way, 8a plus 6b plus 4c plus 9d. Okay. Right hand side would be 4. And why the sign is greater than equal to? Can anybody tell me now? Why this sign is greater than equals to? Yes, from x3, Yash is correct. Yes, very correct. Nirav is very correct. X3 is less than equal to 0. So it's an, unusual thing, right? Less than equal to, according to our standards. So x3 less than equal to 0 is unusual. So corresponding constraint has inequality, which is also unusual for maximization. For maximization, less than equal to is usual and greater than equals to is unusual. Okay, so that's why it is so. So this is where I can create a dual, and this I explained you, right, in a brief. This let me tell you how it is correct. Okay, you can do this by just following the rules, but why it is correct? Okay, let us see the in detail related to that. Okay, so the same question. Okay, and how to convert it to dual. So what we'll do is first we'll take this x2, and this can be written as a subtraction of because x2 is unrestricted, you can write it as a subtraction of two non-negative numbers. Okay, x4 minus x5, both are non-negative. So I replace x2 in place of that x4 minus x5, both x4 and x5 are non-negative. So what will happen? This x2, if replaced by x4 minus x5, so what it will be? 8x1 plus 5x4 minus 5x5 plus 4x3. Okay, plus 4x3. And also you have to replace it everywhere, right? So here, here, and here, and here, everywhere. So if I replace this, I'll get this thing. Okay, I'm not going to speak that. Just the difference is this thing. x2 equal to x4 minus x5. x2 is gone now. So I have now x1, x4, x5. All are non-negative. x3 is non-positive. Okay, but still this is not desirable. x3 less than equal to 0. So what I can do? I can take a negative of x3. So, and let us give it a name x6. So since x3 is negative, so x6 would be negative of negative, it would be positive. So I replace in place of x3 minus x6. Okay, x6 is minus x3. So in place of x3, I will put minus x6. So here there will be a change, and here there will be a change. It will be minus 8x6, minus 6x6, minus 4x6, minus 9x6. And x6 would be positive, this will vanish. Okay, so that would be the change. Okay, so till now we have done two things, right? In place of equal like unrestricted variable, we have rewritten as a subtraction of two variables. That was the first thing. And if it is a negative variable, we take a positive variable just by negating a sign of it and changing appropriately. Okay, so I'll get this thing. So okay, so now the thing is, let me write as a maximization problem. Okay, so let me write in place of minimization, maximization problem, because I want a dual to be maximization problems. So what you can do is you can just change the sign of everything. So this, it will be minus 8 minus 5x4 plus 5x5 and plus 4x6. Negate the sign and convert from minimization to maximization. Okay, so I'll get maximization minus 8x1 minus 5x4 plus 5x5 plus 4x6. Okay, so everything is changed. And now one more change I have done, that replacing this equation, okay, by two inequalities. So I write it as like 4x1 plus this equals to 12. So it's less than equal to 12 as well as greater than equals to 12. I told you that thing, right? If it is 2x plus 3y, okay, is equal to 12, I have to replace it by both the ways, 2x plus 3y less than equal to 12 and 2x plus 3y greater than equals to 12. Which means both the constraints should be satisfied simultaneously, means it is exactly equation. But I can rewrite it like this. Okay. So then I can multiply the second one by minus both the sides. So inequality will change from greater than equals to, it will become less than equal to, and you know this. This is how I converted the first step. Same way, I want less than equal to, so I multiply both the sides by minus, and which will change this to less than equal to. Okay, and so this will be the thing. Other things are fine. The next constraint is fine. Next to next constraint is not fine. So again, I negate it, both the sides, and then I get this. So now you see, it looks like a maximization problem with all the variables non-negative and all the constraints less than equal to type. Okay. So now I can easily, so now I know how to do this. Okay. Because when starting duality, we started from this. Okay. So this is a standard template, right? Maximization, all constraints are less than equal to type and variables are non-negative. I can easily convert it to dual. So let me convert this to dual. Okay. So this is a primal actually. Okay. This is a rewritten problem. Original problem, I rewritten it in this format. So now this is my primal. Okay. That's why I written primal over here. So now if you know this, how to do this. Okay. So according to previous example means we covered in the first, second session. Okay. So I can easily do this. What I can do, there are 1, 2, 3, 4, 5 constraints. So there are 5 variables. Y1, Y2, Y3, Y4, Y5. I give it the name like this. So it's a primal is maximization. So dual will be minimization. So 12y1 minus 12y2 minus 9y3 plus 10y4 minus 7y5. That way. And dual is minimization. Why? Because primal is maximization. Okay. And then you can write a constraints, right? 4y1 minus 4y2 minus 7y3 plus 8y4 minus 3y5 greater than equal to minus 8. Because it's a minimization, so normal thing is greater than equal to. So everywhere you see it's a greater than equal to. And same way, second constraint you can write from this and this, third from this, fourth from this. Okay, I'm not speaking these things, right? So you can easily convert this. Okay, I hope everybody is clear up to this. Nirav, Yash, Priyank, Abhi. Yes, okay, fine. So now you see, okay, so now we just do some arithmetic so that we want a desired answer, right? So that's why we are doing this. Okay, see, I am just proving that whatever directly according to rules is correct. Okay, so you will ask why this all stuff. Then I just want to show you that rules are correct like this. Okay, so so this is done. All variables are non-negative. Okay, and now you see here I can combine these two. So now I'm doing reverse process. Okay, I'm combining these two, and so that I can make an equation. Because you see the second and third, this shaded area, okay, just all they are different in -5 and +5. So this means if I combine these two, I will get an equation 2y1 okay, minus 2y1 plus 2y2 plus 5y3 minus 5y4 plus 7y5 equal to 5. Okay, I cannot have a negative on this right hand side. So what I will do, I multiply both the sides by negative, second one. So once I multiply both the sides by negative, this minus of minus will become plus, and this inequality will change to less than equal to. And then I can combine both the things to an equation like this. Okay, rest things are same. First is written same, fifth is written, fourth is written same. Okay, so that way I just converted this to equation. Okay, now you notice something. Y1 minus y2 is common if you see in the objective function or constraint. You can take 4 common, -2 common, -8 common, 12 common, and y1 minus y2 is common, right? So what I will do, y1 and y2 are not negative, but I write it as a subtraction of these two. So since I am writing as a subtraction of two non-negative numbers, okay, that new number is unrestricted. So y6 will be unrestricted. So I replace y1 minus y2 as y6. So it will be 12y6 minus 9y3. Rest of the things are same. Just the difference is y1, y2 will vanish. Y6 is unrestricted, and everywhere I just change it, reflected it. Other variables are still y3, y4, y5 are still greater than equal to 0. Okay, now let me do one more thing. What I will do, you see everywhere there is a I mean y4, if I take negative y4 is equal to y7. Okay, so in place of y4 I will put minus y7. Wherever it is y4 I put minus y7. Okay, so it will be minus 8y, minus plus over here, and plus 4 here. Okay, so what will happen, y4 is positive, negative of y4 will be negative, so y7 will be like this. You will quickly know why I am doing like this. Okay, y6 is unrestricted, y7 is less than 0, still y3 and y5 are still positive or non-negative. So hence I get this. Okay, and so this is just I reached the solution. Now what is the thing is I have to rewrite it as maximization. So what I will do is I will just change this minimization to maximization problem by just changing the sign of the objective function. Okay, so I'll take minimization to maximization. So minimization to maximization, change the sign. So it will be minus 12y6 plus 9y3 minus 10y4 plus 7y5. Okay, and this all constraints are I mean, these all constraints are just the first constraint I negated both the sides so that I get positive. Okay, so sign of the greater than equal to will become less than equal to. So minus 4y6 plus 7y3 plus 8y7 plus 3y5 less than equal to 8. The second as it is, and the third again I took a negative both the sides, and I got this 8y6 minus 6y3. You can correlate, it's a negative. Minus 4y7 minus 9y5 less than equal to minus 4. Okay, as you know, y6 is unrestricted, y7 is less than equal to 0, and y3 and y5 is greater than equal to 0. And the last change that I am doing is just renaming the things. Let me full screen this. Okay, just renaming these things. Y8 equal to minus y6. So what will happen? Still y8 will be unrestricted because y6 is unrestricted. You take a negative of that, it will be still unrestricted. But the sign I am changing, so it will be maximization 12y8 plus 9y3. Everything is same. In place of y6, I will put minus y8. Okay. Okay, and now you see this is what is our answer. So I have just renamed the variables like y8 is A, y3 is B, y7 is C, and y5 is D for making it nice, right? So it will be 12A plus 9B plus 10C plus 7D. Okay. And then, so y8 is equal to A, y3 is equal to B, y7 equal to C, and y5 equal to D. Okay. And so hence I get this. Okay. So hence I get this, and which is what we have written, right? So this is the maximization problem. These three are constraints. A is unrestricted, B, T are non-negative, C is negative or 0. This is the final answer, which is same as what we have obtained here. So see, I've done lot of steps there. Okay, first I converted primal minimization to maximization. Okay, and then dual then converted to dual, and then again change the objective function. All these steps are just done to show you that the equations translated to unrestricted variables okay, so the equations are translated to unrestricted variables, and that is what I wanted to show. Are you getting this? Or this maximization to minimization, minimization to maximization, conversion, negative taking, and everything, every stuff is just done to demonstrate that this process can be followed to get the dual. But rather than following this entire tedious process, I can just apply the rules and get the dual. Getting this, Priyank, Abhi, Yash? Yes. What about others? There are approximately 100 students, right? Guzar, Neville, Janil, Keval. Yes, yes. So remember the rules, and you can directly convert the primal to dual or vice versa. Okay, although I want to mention one thing. This dual is a very powerful framework, okay, for solving linear program. Okay, many a times, okay, rather than solving primal problem, dual problem if you solve, it would be very much convenient. And you see, the solutions, the value, maximum or minimum value that primal and dual going to give for the linear program will be equivalent. And there is also interesting thing. So if you know the solution of primal, you can also get the solution of dual. By solution, I mean values of variables. Okay. If you know the values of variable for primal, if known, okay, okay, then you can easily get dual variables or vice versa. Okay, so many times rather than solving primal, uh, for many reasons, it is like time or I mean efficiency purpose, we can convert the primal problem to dual, solve the dual, get the values of variables for dual, and using simplex, definitely you can apply the simplex algorithm on dual and then solve the dual problem. But there is a nice thing, uh, just for your knowledge, that there is something called a weak duality theorem. Okay, weak duality theorem tells you if you know the solution of a dual, you can easily get the solution of a primal or vice versa. So no need to solve the two things differently. Okay, you solve one, you get automatically applying the theorem, you can always get the other thing. Okay, so I hope you got the applications of dual. Why is it required? Yes, Priyank. The solution is same means don't get confused. Solution means are you talking about variable values, Priyank? No, yes, Z will be same. That would be same. Right. For linear programming, remember again I am speaking. Listen carefully. For linear programming, primal solution at optimal and dual solution at optimal are same, means the Z is same. But definitely, Priya, the variable values are not same, because the variable number of variables are also not same, right? Primal may have 5 variables, dual may have some different number of variables, because variables of dual related with the constraints of primal and vice versa. So the number of variables are not same, so means solutions are also not same. So actual solutions are not same, their Z values are same. But definitely, if you use some theorems, then from dual variables, you can get primal variable values or vice versa, and that is there. This is just for your knowledge. It's not the part of your syllabus, but it's just for your knowledge. Getting, Priyank? Yes, others are also clear what I'm saying. Solution means variable values are not necessarily same, right? Z value is same, okay, but using some theorem you can convert the values of dual variables. If you have, you can get a primal variable values or vice versa, and that's why people follow this primal, they convert to dual, okay, then they solve dual, okay, Z is same. So that means objective final value, minimum or maximum value, that will be same whether you solve primal or dual for linear programming. Okay, but using, as I say, the weak theorem, okay, weak duality theorem is there. You can get values for primal variables, which is also optimal value. Okay, optimal value. So that is a thing. So this framework is that way very much useful. Okay. In future, you will come across this word primal and dual. Okay. Most probably in machine learning. they will use this in SVM classifier. You will come across these words, primal and dual, but it is not a linear programming. There it is a quadratic programming. Okay, and the quadratic programming means objective function is quadratic. Okay, that is not a linear programming, but I mean, you can correlate at that time. Okay, these things, the concept of primal, dual, etc. are similar. But quadratic function means in objective function there are x square, y square, x1 square, x2 square, this kind of terms are there. So whenever you study that support vector machine, okay, primal and dual will again come in the picture. There you should correlate these ideas there also. Are you getting me what I am saying? This is a nice application. If you are really concerned about application of everything, this is a very nice application. Okay. Others are present or not? Only one person is responding. Yes. Yes. Okay, fine. I hope there is no acknowledgement means you get, okay? Right? Nothing. Fine. So remember this, primality and duality plays a very important role in optimization problems. For linear programming, both primal and dual are equivalent. Okay, remember this. And its application you will learn later in the future. But then don't say that you haven't learned primal and dual. These things I already shown. Okay. So now, okay. Let us take, okay, one more problem which is left last time. Okay. The graph coloring problem. Okay. Can anybody tell me what is a graph coloring problem? You are aware of this. Where did you learn this graph coloring problem, and which algorithm you studied for this? Any idea? In fourth semester, did you study this topic, graph coloring? Yes, Urjit is saying correct. No adjacent nodes should have the same color. Okay, two adjacent nodes of a graph cannot have a same color. Okay, Urjit, which concept you have applied to solve graph coloring problem? I mean, which algorithm design strategy you applied to get the solution of graph coloring? And no one? Dynamic programming, greedy, which one? I am asking about that. Algorithm design strategy means DP, greedy, branch and bound, which one? Very correct. Others agree with answers of Sagar and Yash? Backtracking? Yes. Okay. So in that, it was a simple case, like you start from one node, color it, go ahead, choose the node, okay, such that it is not similar to the adjacent nodes, and try other options. If not successful, go back, try other options. That way you have seen. I hope you know that. Okay. And there, if you have seen the analysis, it was an exponential time solution that you obtain, right? Even if you perform backtracking, you get some benefit because you don't traverse everything. Okay. Bound function you apply and you don't do brute force basically. But still, it's not an easy problem. Do you agree or not? It's not an easy problem if the graph is large. Yes? Yes. If the graph is very large, that means the number of nodes and edges are, I mean, more in number. It is very difficult to solve this problem efficiently. So my objective is to make a linear program of graph coloring problem. Okay. So please pay attention how to make a linear program for a graph coloring problem. So you will say, why to make a linear program for graph coloring problem? So I can also use simplex to solve graph coloring problem. Are you getting the idea? Yes. If you have a linear program, created from the graph. So given a graph, you can create a linear program. What is an advantage? I can use the simplex algorithm that we have seen to solve this linear program, and thereby you will get a solution of graph coloring problem. Getting the relation between this? Yes. So let us see the graph coloring problem. Okay, so please see the notations. Okay, so you are given one graph, G is equal to VE. Okay, goal is to find the minimum number of colors required to color a graph. It's an optimization problem. Minimum number of colors I want to require such that, as you said, no two adjacent vertices have the same color. So all adjacent vertices, that means connected by edge, okay, should have a different color. Okay. So what are the variables? Okay. Can anybody just tell me, before I tell you the solution, can somebody tell me what would be the variables like x1, x2, x3, x4? Just we have learned. Can you tell me the variables here? Should I have, I mean, a variable for what? Any idea? For color? Okay. So, since you are trying to minimize the number of colors, okay. And color refers to what? Color refers to what? To what you are giving a color, Urjit? Node, very correct. Nodes, very correct. Okay, so we are giving a color to node. So the nodes are very important. So can I say for the nodes you should have variables? Yes, let's see. Okay, so there will be a variable of kind xij. Remember the notation xij. This is a variable. What it indicates? Remember this notation, node I is given a color j. If it is so, xij value is 1. It's a Boolean value. If it is not, it is 0. So if the node I, so you have a graph like this, okay, like this, okay, and there are, let's say, 3 colors, okay. This is a node number 1. So x11 is equal to 1, which means first vertex, vertex number 1, can you give it the color number 1? If yes, then it has a value 1. If no, then it has a value 0. It's a Boolean value. So if vertex I, if you can give a color j, then xij would be 1. If not, it would be 0. This is a simple thing, okay? Right? This is one kind of variable. So means if there are, let's say, I'm talking about 5 vertices, and let's say I'm talking about 3 colors. I am just taking 3 colors, red, green, and blue. I have 5 vertices in a graph. How many variables will be there? How many variables will be there? Getting my question? No. No. 15. Very correct. Getting why, Ronak? Because for every vertex and for every color, you have a combination, right? Can you color vertex 1 with color 1? Yes or no? There is one variable. Vertex 1 with color 2, vertex 1 with color 3, and so 5 into 3. Very correct. So total 15 variables are there. So that we have to determine, Rishi, that which, so it's a variable means it has a value 0 or 1. So means whichever is 0, I mean, which means that color is not given. But we have to, yes, those constraints are there. We will see. Okay. But 15 variables will be there in a program. Yes or no, Rishi? Okay. Yeah, that will be followed. Let me finish, then we will see. Okay. Let me finish with the entire problem, then we will see. Okay. Okay. So see, as you said, Rishi, this is also there. The Wj are the variables which indicate whether any nodes in a graph which is assigned color J or not. See, this is very important. When you can say Wj is 1, if there is at least one node which is assigned a color J. Okay. So in any node, if you have used color J to get the solution, Wj will be 1. So that means how many such variables will be there? Okay. So as there are colors, okay. So if you have 5 colors, or sorry, 3 colors, then there are 3 variables, W1, W2, W3. The W1 says I am going to take a 1 value if there is at least one node which is given that particular color, first color. W1 means if any vertices is there which is given color number 1, then it will be 1. Otherwise, 0. This is second type of variable. Now, you see, objective is to minimize the number of colors. Okay. So what I will do, I will write it like this: minimize sigma wj. What do you mean by that? Let me tell you. Yes. So if there are 3 colors, okay, I have 3 variables: W1, W2, W3. Okay. And this all variables take which value? Yes, Rishi? What are the values that Wi's can take? 0 or 1? Yes. So that means sigma of W's, Wi, okay, if there are 3 colors, which will be maximum 3? Am I saying correct or not? Yes, it would be a maximum 3. So the total will be less than or equal to 3. And I want to minimize. So that means I want to find out this sigma wj. I want to find the assignment such that the sigma wj takes a minimum value as possible. As minimum value as possible. Are you getting this? Why the objective function is minimize sigma wj? Yes, Yash, Rishi, Priyank. Right. Okay. Okay. What are the constraints? Okay, now carefully look at the constraints. Okay. This linear program is actually somewhat difficult compared to previous one. Okay. Because there is no graph given. I am writing in general, right? Okay. For any graph, I am writing this. That's why. Okay. So you see this one. Try to understand this. Sigma xij is equal to 1 for all I belongs to V. The summation is over J. So what this tries to say? Keep I fixed. For example, let me take I is equal to 1. Let me take I equal to 1. And where I J? Very okay. So what is J? J is a number of colors, right? So there are 3 colors. So what it will be? X11 plus X12 plus X13. I is fixed. Remember, I is 1. So Ij. Okay. So X11 plus X12 plus X13. That is a sigma Ij. And that should be equal to 1. Why? Why, Rishi? Can you tell me the reason? Exactly one color, Priyank. Not at least one color. Right? At a time, you can give only one color in any one solution. One node, one color. Now are you getting your answer, Rishi? That first vertex, okay, so x11 is either 0 or 1, x12 is either 0 or 1, x13 is also 0 or 1. But see, my constraint is the sum of x11 plus x12 and x13 is 1. Why? Because exactly 1 will take a value of 1 and 2 will be taking the value of 0. Am I saying correct or not, Priyank? Right? Yes. Okay. Okay. So means every vertex will, and this should be true for every vertex I, right? So if you have a 1,000 vertices in your graph, and this constraint should be, so how many such constraints will be there? This we have seen for I equal to 1. So similarly, how many constraints will be there of this type? Getting the question? I wrote in the chat box that for I is equal to 1. So this should be there for every I belongs to V. That means I'm asking number of nodes. Very correct. So as there are number of nodes, those many constraints will be there. Yes, for each I, for each vertex. That means for each vertex. So such, if you have n vertices in a graph, there are n such constraints. Okay, of type x11 plus x12 plus x13 is equal to 1. Same way for x21 plus x22 plus x23 is equal to 1. Same way you have to repeat for every vertex. That is for every I. Okay. So remember, the objective function is to minimize the number of colors. That means minimize sigma wj. One constraint would be only one color can be given to one node, and this should be for every node. Okay. Any other constraint? Yes. So another constraint would be, let's see is a set of colors, and there is an edge from U to V. So U to V is an edge. Okay. There is an edge from node number U to node number V. Okay. So if there is an edge between U to V, then jth color can be given to at most one of it. Adjacent cannot be given the same color. That is your prime focus, right? That if there is an edge between U and V, okay, U and V cannot be given same colors. What does that mean? X, U, J. What is J? J is any color. Okay. If U is assigned a color J, okay, what is the corresponding variable? XUJ. Node number U given a color J. The variable is XUJ. It can take either 1 or 0. This is either 1 or 0. Same way, node number V can XVJ, that can take 1 or 0. If you add them, okay, you should get maximum 1 because U and V are associated by age. So if you give XUJ is equal to 1, okay, that means you are giving a jth color to U vertex. You should not give, you must not give jth color to V vertex. So that means for every age U comma V, XUJ plus XVJ should be less than equal to 1, and this should be for all colors J, right? Okay, you tell me how many, so if you fix an age U comma V, how many such constraints will be there? I take a 1 U and V. How many constraints will be there? I repeat my question. I fix U comma V. So if I fix U comma V, how many such constraints will be there? No. No. Vidur, no. Number of colors, yes, very correct. Are you getting Vidur? Why? Why? Because I have, if you fix U and V, the variable thing is only J, and J is a color. And you have to take every color. Yes. I hope that is clear, right? Right. Yes. So, okay. And so number of colors. And if you vary it over all ages, then how many total combinations? Yes, Vidur, Urjit, can you tell me? This is just for one age, right? This you have computed for one age, Urjit? For one age, you have how many constraints like this as the number of colors? So you have how many ages? How many ages are, yes, very correct. You have whatever the number of ages, like E is the number of ages. Okay. Now, so those many colors are required. Okay. Multiplied number of colors, and those many constraints of this type are required. So remember, the graph coloring is a very hard problem. Why? Because it has many constraints. It has many variables. Okay. And one more thing, okay, that we forgot is for every I in the vertex, I is a vertex, right? And J is a color. Remember, Xij, I is vertex, J is color. Xij should be less than or equal to Wj. Okay, definitely this should be there, right? Because Xij can take 0 or 1, Wj can take 0 or 1. But it should not be like that. X12 is 1, okay, and W2 is 0. Is it possible? X12 is 1. Is it possible? No. Why no? Why no? Because W2 is 0, which means you haven't used color number 2 anywhere in this graph. W2 is 0 means never used color 2. And now you are saying color 2 is given to node number 1, which means x12 is 1 means you are giving color 2. So that contradicts. So this should not happen. Yes. And to avoid this conflict, okay, we should add one more constraint, that xij should be less than or equal to wj. And this should be for all vertex, for all colors. That means total such type of constraints will be vertices into colors. Okay, this type of constraints, number of edges into colors. Okay, this type of constraint, okay, one for every vertex, number of vertices. So you see, and then that will become a linear program. Then you have to convert it somehow to the standard format, and then you can use a simplex. So are you getting the difficulty level of the graph coloring problem? Yes, Rishi? Okay, so that's why I taken this example here, because from tomorrow onwards we will see approximation algorithm. It would be too hard, okay, to solve such problems on a larger input size. So we need something which runs efficiently. For that, we need approximation algorithms. That is, for solving hard problems, to solve hard problems efficiently, okay, we need something called approximation algorithms. Okay, so we'll see various hard problems and their solutions. Okay, and we will prove that these approximations are good actually. So pay attention in this session, otherwise the proofs will not be clear. Okay, up to this, any query? Are you getting this up to everybody? Yes. Okay. Yes, people are reduced by a factor of half. Okay, so fine. We'll see tomorrow. Thank you so much.